I'm just trying to click. There we go. Oops. Hang on a minute. Let me just go back to my PowerPoint. Yeah. Here it is. That's better. There we go. Okay. So my focus is research-informed pedagogy, underpinning teaching for mastery, as it was. And as I begun to prepare this, I thought I'll focus in on teaching with variation. So one of those 5 big ideas that was just mentioned. In the time that we've got, I thought let's focus in on one aspect. I'm taking quite a lot. This is a research seminar, so I'm particularly underpinning it with research, which I always like to do, and so we're going to focus in on variation, as I just said, and we're going to. There are just as background information. There are 2 main frameworks of variation. Variation developed independently, both in China, in Shanghai, and also in Europe. So you may have heard of somebody called Marton, who was a lead for one of the frameworks. That was the European one. And then there's also Professor Gu and others, and Dr. Huang and etc., who looked at variation in China quite independently. But those 2 branches have done some work together. There are things that are the same about them. There are things that are different about them. And just to clarify that I will be speaking about the Chinese one, Bianchi Zheqiu, and I just hope there's no Chinese speakers here because I know I've not pronounced that correctly. But basically, it means teaching with variation, which is central to teaching in Shanghai and broader China, and is very successful in teaching mathematics. And this is the book that I've drawn the main research from, which is a collection of essays from lots of researchers, including Anne Watson and John Mason, who are English researchers who you may have heard of. Right, and my computer's got a bit stuck. Here we go. Okay, I'm going to ask you, are these statements true or false? And I want you to put in into chat T for true, F for false. So what's about the first one? Okay, and I'm going to ask you just to wait a few seconds, put it in, but don't press enter. And then we'll have what we call a chat blast of that. So let's have a think about this first one. Conceptual variation is about learning mathematical concepts. What do we think to that one? And I'm going to go 1, 2, 3 and enter. Okay, what's coming out in the chat? Anything? Can people hear me?
Yes. Can you see the chat yourself, Debbie, or do you want me to tell you?
I can't. No, I can't see the chat. No.
Okay. There are it's mixed. Quite a lot of falses and quite a lot of trues. I would say it's roughly about 50-50 looking at the chart.
Okay. I'm not going to give you the answer, but I'm going to ask you the second one. Okay. So the second one, maybe if you just put a P for this one so we can distinguish between the 2. Procedural variation is about sorry, I realized I put 2 abouts in this, is about learning about mathematical concepts. Procedural variation is learning about mathematical concepts. 3, 2, 1 and enter. Okay, what have we got this time?
Lots of falses this time.
Lots of falses that time. That's good. I'm pleased you said lots of falses because this one is false. Let me just
most of them are false now.
Most of that's great. Okay, that's good. So I've just got a quote here from that book. That's why it says page 6. So both conceptual and procedural variation tasks are used to develop mathematical concepts. So it's all about developing deep conceptual understanding, both procedural and conceptual variation, and to experience those critical aspects due to what the teacher develops. So looking at the appropriate dimensions on conceptual and procedural variation in the classroom develops understanding of concepts. So well done. I'm impressed. That's good. And okay. I try to distill variation into something very simple. When I was working with teachers, I found they were finding it hard, particularly the procedural variation. But actually, you can just think about variation, both procedural and conceptual, as influencing the way children think. And we do that through what we keep the same and what we change, in order to draw attention for all children to focus their attention on those essential features. So they all see those key mathematical ideas within that. So that's kind of simplified, but I think it's helpful to think about variation. Sometimes people get confused between the two. If you do, it doesn't matter, as long as you understand that it's about what we keep the same, what we change, and in particular, it's about stimulating children's thinking and drawing attention to particular features of mathematics. So I've got two up here. I've got two comparison. So I've got conceptual variation on the left, and I've got procedural variation on the right. If in the alphabet your surname comes after J, can you focus on, well, let's do the first bit of the alphabet. First bit of the alphabet up until J, focus on conceptual variation. And after J, if your surname begins after J, can you focus on procedural variation? And all I want you to do is to read your little bit and just put in even just a little bit of what struck you, or what you think is a key feature of either conceptual variation or procedural variation. Okay, whatever is. So just let you give you a minute or so to read, and then just when you're ready, start putting in the chat box what you think it is you've read. What is conceptual variation and what is procedural variation? So we're using those two terms now. Or if you'd rather speak, then you can just put your hand up. I'm very happy for people to unmute and speak. So when we've got some things coming through in the chat, if you could just let me know.
I think everybody's thinking very hard.
Everybody's thinking very hard, yeah. And you've got to have time to read it as well. So the people after J are doing the procedural, and the people with surnames before J are doing the conceptual. Just might want to pick something out of the quote that struck you.
So, so far, a couple of answers around procedural variation.
Yeah,
One
great.
of them is that procedural is looking at small changes in the process of completing a problem.
Yep.
That it's the ability to discriminate which rules lead to which outcomes. Right. The ability to transfer strategies and make connections to different concepts to solve a wide range of problems.
Yep, lovely.
Procedural spotting patterns.
Yep.
Strategies, connotation of concept to aid understanding of multiple perspectives. And so conceptual, I've got one answer for conceptual here. So obviously we've got requires a variety of ways of looking at a concept. Thank you, Dom.
Yeah, great. Thank you. Some good answers there. Certainly conceptual. Yep. Looking at different ways of looking at a concept. And what I heard in the procedural variations was lots of verbs like connecting, transferring, and because procedural variation is about the dynamic process And there you will see that, you know, at first they were thinking about conceptual variation, but then Professor Gu said, well, actually, mathematics is dynamic. It's a process. We move through. It's that thinking process. And so therefore, in the classroom, we need to stimulate that thinking process, you know, in that logical way, moving from this to this, and this makes sense because of this. So it's that thinking process that is really at the center of procedural variation, whereas conceptual variation is about representing the concept when you're teaching in the classroom. How am I going to represent this concept? What am I going to use? A number line? Am I going to use an array? What am I going to use to represent this concept? Am I going to use a tens frame? And so then you choose that, and you choose in the lesson that we're going to watch in a minute. A teacher chooses she chooses some matchsticks, and like you'll get to it in a minute, you'll understand what I mean. But she also chooses a number line partway through the lesson as well, which enables us to look at the concept in a different way with that. So thank you for doing that for me. That's got us really thinking about procedural and conceptual. And here's just a quote. I love this phrase, the non-arbitrary. It emphasizes and draws attention to the non-arbitrary. It's not by accident. I want the children to see this aspect. I want them to see the relationship between what they know already, and to connect it to the new learning. And they argue that conceptual variation could help children understand the essence of a concept, looking at it in different ways. Meanwhile, procedural variation could help students develop well-structured knowledge and non-arbitrary connections, those dynamic connections between different types of knowledge. So there's got that static element of conceptual, and you've got that dynamic element of procedural. I just pulled out these quotes as well from the research literature, because I think this is very important, that variation develops mathematical thinking through procedural variation, also through conceptual, but I think in particular that dynamic process. And I've just pulled out some quotes which show this, that the green one at the top that focuses on developing problem solving and building a well-structured knowledge base. And when you're solving a problem, you need to think, where shall I start? What shall I do next? What would make sense to do next? So you're involved in that dynamic process. The blue one, mathematical thinking methods reflect the simplicity and convenience of logical connections. Oh, I can see this. Oh, of course this is. And you'll see some of that when we look at the lesson. In the red one, when designing applications or contexts, it's critical to consider if they could motivate student learning. Are student curious? Are they looking for the next step? Are they looking for the next connection? I say, is their cognition being stimulated? Is their thinking process being stimulated? Or are they just listening to the teacher and thinking, this is what I've got to do? Or are we stimulating them to think for themselves in a controlled way in which we particularly focus on particular aspects and direct their attention to? And this is my favorite quote, or one of my favorites. I'll show you the other one at the end. The teacher is advised to avoid mechanical repetition, but instead to create an appropriate path for practicing the thinking process. So procedural variation is about practicing the thinking process with increasing creativity as children become more confident. So there's various terms used in variation. We've just explored conceptual variation, that static way we represent a concept, whether that's a number line or a tens frame or 100 square, etc. Procedural variation, that's a dynamic process, that logical thought, those small steps as we progress through the learning. Anchoring knowledge point, haven't mentioned that yet. Anchoring knowledge point is our starting point. The anchoring knowledge point needs to be what children already know. It needs to be a point that everybody knows this, but this is going to be really relevant to the new learning. So let's all start here where we can all get on board, and then we'll take all the children with us. Potential distance. Professor Gu's research, the Qingpu experiment, found that actually the smaller distance between steps, between the existing knowledge and the new little bit of knowledge, the smaller the step is, the more successful it is in all of the class making good progress. Pudian means scaffold, but it has a slightly nuanced meaning. It's a Chinese word, And it's got a hierarchical sense that we start from where children are, or we start with simple examples, and then we build into the more complex. But the early stage is about providing that scaffold in order that children can, develop their confidence, develop that knowledge base, and then we can, give them something more complex. Core connection means that I have that thinking process. There's a connection that runs through this that I'm building and building and building on, and it's making sense to me as I go. A learning trajectory is something similar. It's the order in which we put the sequencing of learning. Clements and Sarama, who you may have heard, who do a lot of research in early years and early mathematics, reception earlier than that in Key Stage 1. They did some research, and that actually, if you take some activities around a topic, one group just did them in a random order. They all enjoyed those activities. One group did them in a carefully sequenced order. And as you can guess, the group that did them in a carefully sequenced order did better. Same activities, but because of the order, we established that thinking process, that making sense, that core connection running through. So they're just some terms in variation. So we're going to get on to now the lesson, which I'm going to show you a couple of clips from. But this is year 4. I'm just trying to think which year it was. I think pretty sure it's year 4. The unit they're working on is division with remainders. This is at the beginning of that unit. It's a 2-week unit in the NCTM curriculum prioritization materials. I mentioned curriculum prioritization materials. It is a full curriculum, but we highlight the most important bits. So this is year 4. So first of all, they've got 21 sticks and they're asked to make triangles. I'm just going to give you a minute pretending you've got 21 sticks. I know you probably haven't. It'd be amazing if you have, but you probably haven't. But you can draw 21 sticks, but make them into triangles. Okay, so just make them into triangles. Just draw 21 sticks. How many triangles can you get? Okay. So hopefully you've been able to do that. And so what was going on there? This is the start of a lesson. Teacher just said, with your 21 sticks, make some triangles. Everybody could do that. Everybody was there, and everybody could identify that we ended up with 7 groups of 3. And that became a STEM sentence then. And they all said that, and they could all see the structure of 7 groups of 3. So using the triangles was an example of conceptual variation using the matchsticks. They exposed the structure in a particular way as 7 groups of 3. And also the STEM sentence is also another element of conceptual variation of the mathematics. We're representing those 7 groups of 3, both with an image, with the physical sticks, and also with the STEM sentences, 2 things that go together, and the children can see the structure of those 7 groups of 3 in there. So that's our starting point. Procedural variation, not a lot in there at the moment. That we need to start moving through the lesson to pick up on that procedural variation. So let me just go to my next slide. Right, okay, I'd like you to draw now. You'll have to draw it again. You can't pick up and move your matchsticks. But now, still got 21 matchsticks. Make some squares and just type into chat what you've made. How many squares have you made? And what do you notice? And what do you think the procedural variation is going on here? What are we going to draw attention to? Okay. Any answers in chat? Not yet.
Not yet. We haven't got any answers in the chat. I don't think anyone's brave enough yet.
Okay. I don't think this is hard. The children didn't find it hard.
Yeah.
So
okay, we've got 4 matchsticks needed per square.
Yes.
And then we've got 5 squares and 1 stick left over.
Yeah, we've got 5 squares. So we've got 5 groups. So we went back to our STEM sentence again. We've got 5 groups of 4. What the children didn't know at that stage was how to explain what was made. They just said was left over. And then the teacher introduced the word remaining. So we had a new STEM sentence then built on the last one. We have 5 groups of 4 and 1 remaining, and they could see that. And I'm going to show you, I'm hoping it's going to be all right. It will depend on your personal internet, I think, but I'm going to show you the children doing that now. And what I want you to look out for is what the children are saying, because that's the procedural variation. What connections are they starting to make? We said procedural variation is about making those connections. So let's just go and let's just listen out for the children's reasoning and their making of connections. Can you see my screen okay, the video?
Okay, this time, same again, easy peasy, just make squares this time.
Yeah.
We're going to do it nice and fast this time. Separate squares, off you go. Quick, quick, quick.
You can't make flaming squares. There's going to be extra matchsticks because we don't have enough to make enough squares. Because 21's not in the 4 times table.
Yeah, it's not. 21's not. 21's in the 3 times table. Yep, there's not enough. Yep, there's one more left.
Okay, I'm going to just stop there. So what did you hear those children talking about? What was going on there? Somebody else, somebody unmute and just tell me, what did you notice about what those little girls were saying?
We've got something in the chat. People talking about its times tables.
Yes.
21's not in the 4 times tables.
Yeah. Yes. Yeah.
That means she's saying probably it's not divisible. It's not something that you can easily.
Yeah.
21. Yeah.
It's not divisible by 4. Yeah, not
exactly.
divisible by 4. Absolutely. Yes, it's not in the 4 times table. So they're already, even before they've made the squares, they know, they're making that connection that there's going to be some left over. They know because 21 is not in the 4 times. So already that reasoning is kicking in. You know, that reasoning process that Professor Gu talked about is happening, isn't it? They're already really, because of the activity, because we did no remainings to begin with, and now we're moving on to, it's going to be something remaining. And there's some new learning here. The children are going to be taught what a remainder is for that there. So in terms of then, and they use that STEM sentence, as I said, in terms of procedural variation, this is the nature of the activity linked to the previous one. So we've got that process going on. We've got that one activity. We're linking it now to the next activity, and it's stimulating the children to reason and to see that we've got some left over. So very little was changed. We kept the 21 the same. But we're now using squares, so we've got groups of 4. So the pupils are beginning to think and see in the shapes the structure of that. And the conceptual variation is we've got another image. We've got an image of a remainder. We've got these 5 groups of 4 and 1 remaining. So we can see quite clearly that 1 remaining. And they were saying, because we can't make another square. Because we've only got 1 left. So they're linking that. So they're both procedural variation and conceptual variation happening here. Okay, the teacher then, they say the same STEM sentence together. And then she says, okay, keeping your 5 groups of 4 and 1 remaining, having said the STEM sentence, I now want you to write an equation. Okay. So just sort of type into chat, what do you think is the equation that they're going to write? If you look on the board, it says 21 equals. How are they going to complete that equation, do you think? Just want to type into chat what the completion of that equation?
3 times 7.
Oh, no, they're using the image that they've just got. So they've got 5 groups of 4 and 1 remaining.
Yes, of course. Yes. Yeah. So we've got 21 equals 4 times 5 plus 1.
Yep.
5 times 4 plus 1, 21
Yep.
equals 5 times 4 plus 1,
Great.
21 equals 5 times 4 plus
Yeah,
1.
thank you. Yeah, well done. Yeah. So that's what the children wrote. They wrote that. They did write equations like this when they were first introduced into division or in the multiplication context, I think, in year 2. So they have written equations like this before. So they're drawing on knowledge, but they're linking them to this structure and seeing the structure of the one that's remaining. Yeah. So now we've had, in terms of conceptual variation, we've now got 3 representations. We've got the matchsticks showing the structure. We've also got the stem sentence. There are 5 groups of 4 and 1 remaining, and now we've got an equation. And of course, what the teacher does then with the equation is draw out, what does a 5 represent? What does the 4 represent? What does the 1 represent? What does the 21 represent? So she draws out, ensuring that they and they've got their structures to look at. They can say, well, the 5 represents the number of squares that I've got. The 4 represents the number, how many matchsticks in each one. The 1 is the one left over because I can't make another square, and the 21 is the total matchsticks. So it's really important at that stage to connect those 3 images to the 3 representations to the same mathematical idea. So that's going on there. Okay, as I said at the beginning, they also then look at it on a number line. I like the way the teacher's drawn down the squares as they jump along the number line. And then, of course, the crucial bit is, can I do another whole jump of 4 at the end? No, I can't. I have to do a partial jump. I can just go 1. I can't go a whole jump of 4. So the conceptual variations happening in there. And the procedural variation is connecting this representation to what's gone before as well. Okay. So now they can make any shape they like, write a sentence and write an equation about it. Okay, should we have a look and see what the children do? Let's just go to that video now. I'm going to show you that video. Set my thing. Okay, and oh, I can't see it. I've got this window at the top, which I can't move. Oh, I've moved it. Right, good. All right, now let me just click on this one now. Okay.
I have got a task for you. I would like you to make some more shapes of your choice, or like we said earlier, if it's a big shape and you want to make bundles, that's fine too. And I would like you to represent it with your matchsticks and with an equation on your whiteboard and with the number sentence that you can see on the board. Off you go. Interesting. Some people are building first and some people are writing first. Make sure that they both represent each other, though. They both link. Well done, Nikki.
That's 7 matchsticks in that shape, and it looks like a speech bubble, weirdly. I think I can make 3 because there are 7 sticks, because there's 21 divided by 7, which would be 3. So then there's my last shape. There are 4 of them. And I think they're pentagons. I'm doing 4 groups of 5 this time, not 5 groups of 4. And I'm also going to have 1 remaining.
Morale has 21 is equal to 3 groups of 6 plus 3. Can you figure out how many she's got left remaining on her desk?
3.
3. Well done. Why did you say the 3?
because I know that 3 times 6 is 18. And then to get to 21, you'll need to add 3.
Lovely. So she's got 3 more. That's what it was in the equation, wasn't it? Excellent.
Okay. I'm out of there. Anybody want to unmute and just say what you noticed? Anything you noticed in the video? Be nice.
Hi, Debbie.
Hi.
Should I let someone else speak? Does anyone else want
Yes,
to have a go?
please.
Anyone else want to speak? Otherwise, I'll say something I noticed.
Okay.
So I did notice earlier that Simon had actually written his equation 21 equals. Now we often say when you put the 4 first, it's 4 5 times. So mathematically, we consider that to be more correct because it was 5 squares. So this time, when it was a pentagon, you could have had the same equation, 21
yes,
equals.
You could. Yeah.
And I'd then say maybe we should write it 5 4 times plus 1.
Yeah, so in the curriculum prioritisation materials, which where this lesson comes from, we made a decision that we would teach children both ways, but it was the context that would clarify. So we've got a context here, we've got some images here, so we can see the way the children are thinking. And you can either say four groups of 5, or you can say 5 4 times. So we've linked the language to being still able to talk about 5 groups of 4, and not be bound by you have to write it one way. So 4 groups of 5 or 5 4 times is of course the same thing. And the 5 4 times particularly links itself to when we go onto a scaling structure for multiplication. Whereas the other one, 4 groups of 5, lends itself to multiple addition. So that's all I'll say about that at the moment. Look it up in the curriculum prioritisation materials if you want to look at it more. But we have gone with which is what the Chinese do, is actually give the freedom of children to write it either way. Initially, because we're starting with repeated addition, so when we start multiplication in year 2, we just write it one way initially. 4 times 5 will be 4 groups of 5. Let me talk about 4 groups of 5. But here, by year 4, they can write it either way.
Hello, we lost you, Debbie. Okay.
Can you not hear me?
You know, Simon's responded now just to say that the commutative nature was being developed almost independently in the lesson. So
yes, can you still hear me?
Yes, we can now. You went quiet for a minute. I wasn't.
Okay, good. Okay, I'm glad I'm back. Okay,
Thank
back in
you.
the room. Okay, good. Okay, thank you. Good question. So here, in terms of variation, we're opening out a little as the pupils are gaining confidence, and bringing together the procedural variation. All 3 representations are linked together. So we've got all 3 representations and looking at how they are linked together. So that's the procedural variation, seeing the connection between these all 3 representations. So they've been built up during, if you remember, we just started with matchsticks, just a visual image of the sticks. We then added a stem sentence to that. So we added a language representation to that. We then added an equation to that same thing. And so we've now got 3 representations of that, plus the number line, which we had briefly as well. But here, the children are working with these 3 representations and are asked, and have got the freedom to choose which shapes they make, but they have to represent them in those 3 different ways. We've then got a problem whereby there are 18 sticks and 2 remaining. So they're given some information and they have to complete the equation and also complete the sentence. They don't have to do it with matchsticks here if they don't want to. They can move away from the matchsticks, but they have to do the equation and they have to. Would somebody like to put an answer to that in there? What could the equation be? What bits do we know is what the teacher drew out, and what bits don't we know? Okay. Anybody put an equation that it could be?
Thinking and typing. 4 times 4 plus 2.
4 times 4 plus 2. Yeah, that would work very well, wouldn't it? 21. So 18 is equal to 4 times 4, which gives us 16 plus 2. Yeah, yeah. And so then we'd be able to say the same sentence. So there were 4 groups of 4 and 2 remaining. Yeah. So that's what the children had, and their attention then was being focused on the factors here. They had the 18, they had the total. So they're looking at the equation in a slightly different way. So rather than making the shapes in the same sentence and writing the equation, they're now looking at, I've got some bits of the equation. So you can see how that Pudian is being built up. That hierarchical progression is becoming a little bit more challenging now, but those small steps that the children have had is supporting them, and they were pretty successful at doing this activity. And then
there are a couple of more calculations if you want me to read them out.
Okay.
So there are 4 groups of 4 and 2 remaining, or 18 equals 8 times 2 plus 2. 18 equals 2 times 8 plus 2. 18 equals 4 star 4 plus 2. So there's a number of different ways that are coming through.
Great, lovely, thank you. Yeah, and so there's more than one way, so it's a nice little problem, and the children then compared their ones. The teacher pulled them out, and then they then went to say them as stem sentences as well. Thank you for that. So we're now getting to the end of the lesson, and the children have got a question: true or false? Is it true that the number of remaining sticks can be a larger number than the size of the group? What do you think the teacher wants them to notice here? And she's got an image on the board. The image is important on the board. They don't have to use matchsticks, but they've got an image on the board. Anybody want to unmute or type into the chat? What does she want them to notice? So is it true or false? What would you say? Would you say it's true or false that the number of remaining sticks can be larger than the size of the group? Just want to put into chat, true or false, a T or an F.
Yeah, just true we've got.
Okay.
The groups are 2s, so the remainder cannot be larger than 2. Got false, false.
Yep.
False. Mainly false is coming through.
Mainly falses, yeah, because of course what she wants the children to notice is that although the equation is correct with 18 equals 7 times 2, which is 14, plus 4 is 18, that's perfectly correct. But what she wants them to notice that actually when we've got remainders, we only stop when we've made the maximum number of groups. And so she wants them to notice that, and then that generalization is that will come later. This piece of mathematics isn't finished. They've still got some more lessons on this, whereby they'll be looking at it using division equations. They'll be looking at it systematically, how adding 1 to the dividend each time means that the remainder increases by 1 until we've got another group, and so they work systematically on it. So there's more learning to be going on here. So, but they get on pretty well with that. They're not quite there with them. Some of them are still saying, "Oh," but at this stage that's okay because actually they're going to be doing some more learning with that. So I'm going to stop now and have our discussion and our question time. And in fact, so what struck you about the lesson, and how did it develop and exemplify your understanding of conceptual and procedural variation? So I'm going to stop my share now, which will be nice because I'll be able to see you. So let me just go and see if I can stop my share from my sharing here. Right, okay, and then I'll be able to see you. So if you want to unmute now, if you want to show your video now, that'll be nice to see some faces, so I can see some people. Okay. So anything that struck you or any questions you've got? Anything